Hi there, good morning. Since I have my the breaker panel being replaced today, I have no idea when they're going to come. And as a result, I have no idea when my internet connection is going to be interrupted. I think that the crew is bringing along a generator, but they still have to disconnect. I still have to disconnect um, the plug to the wall outlet to connect to the generator. So there will be some disruption when the crew arrives, and I have no idea when they do. So I'm gonna do today's lecture in a slightly different fashion compared to normal. So what I'll do is I'm gonna do this in a what I would call fragmented synchronous mode, which basically means I'll do segments of recording and post it onto Discord, and then I'll check into Discord and answer questions regarding those your clips. And whenever possible, okay, I'll record some additional clips, and so you guys will just basically be watching without live interaction, maybe for a little bit. It's only for today because I'm getting the once I said as I said, I'm getting the breaker panel replaced. I live in a, let's see, almost 70-year-old house, and the electrical panel that I have has aluminum bars inside, and according to the electricians, it's really just a problem waiting to happen. It's not if it will happen, it's just a matter of when it's going to happen. And when I said happen, it means burning the whole house down, basically. All right, so on to today's lecture. All right, so what we are looking at here, this is the opcode table. And as I said, the opcode table is in the scope of exam 2, so you probably want to have the opcode table handy, but more importantly, you need to know how to read the opcode table. So we have gone through quite a few of these instructions already. And the best way to understand the instructions is really just to use single transitions in LogicSim and analyze the components inside LogicSim and make sure that you understand how the output of ROM, each bit, okay, how each bit of ROM is connected to the individual components, and what is it turned on, how is it configuring the switches, which register is enabled, is RAM enabled, if so, is it reading or write, are we reading or writing, and so on. Okay, so all of those things that I did in class, you probably want to do that on your own, at least to a few of these instructions. All right. I got one question about how the OR instruction is hijacked. Okay, so the idea of hijacking an instruction, meaning that the OR mnemonic and also the increment mnemonic, they are basically the same, and the way it is implemented is in the assembler. So in the assembler, there's a tab called mnemonics. And this is basically a table lookup method. And what the assembler does, which is also implemented in a spreadsheet entirely, is it will go down this list, okay, to look for a match of the mnemonic. And you can see how increment and decrement, they are higher in terms of precedence. In other words, when the spreadsheet looks at this table, it will find increment first before it finds the instruction that it's hijacking, which is OR. So that is the reason why increment has precedence. That's why increment hijacks certain variations of the OR opcode. So other than explaining it this way, it's a little bit harder to explain. If you are a spreadsheet guru, you can go to the Assemble tab and look up, I cannot remember which column now, but they're sort of documented. So if you look up the documentation of one of these columns, it will tell you how the opcode is recognized and how it works. So I cannot quite remember. I think it's column C. So let me see. Yeah, so column C is the opcode index into the mnemonic table. So if you click on this one, okay, which has a kind of gigantic formula on its own, so the way it does is it uses the match uh, formula in the spreadsheet to look up the mnemonic table. And what match does is it will search from top to bottom. It will search from the first row and then move on to the second one and so on. So it finds basically the first match, and that's why the ordering of the mnemonics in the mnemonics sheet of the assembler makes a difference. So if I put the OR mnemonic first before the increment mnemonic, so if I put the OR ahead of row 9, then the hijack will never happen because it will always recognize the OR first. Well, actually, it will still happen because when it sees the increment, it will still generate the opcode for increment. So regardless of the order, it will still hijack the opcode. All right, so that's that. So for that matter, okay, let me just show you one more thing, about the hijacking, because I think this is kind of a mystery to some people. So if I specify increment A, it is going to be D0. If I specify increment B, it's going to be D5 in hexadecimal. Okay, so I put this code in, I go to the Assemble tab, and it is saying that the opcode is D5. And you can look at the RAM file too. RAM file shows you the content of RAM as well. It's definitely a D5. So if I go to source and I use the opcode that it's hijacking, which is the OR instruction, but in this case it will be OR BB. Okay, in other words, it has to be the same register twice. So when I look at this, the opcode of OR BB, it's going to be exactly the same. So the assembler says it is the same, and the RAM file also says it is exactly the same. So this is what I mean by hijacking. So the real hijacking is not so much in the assembler; it is in the it's in the ROM of Logisim. So let me see if I already have a Logisim window up, and let's see. No, I do not. Okay, so give me a second here so I can retrieve one of those. I'm just looking at the history of me running Logisim, and that's the laziest way to get it started again. Okay, there we go. All right. So when we look into the processor in Logisim, okay, there we go. And particularly in the ROM. Okay, so if you right click on the ROM and say edit content, and we want to look up the location corresponding to D5, right? So it's D50 as the address in ROM. So we look it up, okay, there we go. We have a bunch of these. So the entire D family are either or increment instructions. When we specify the same register, which will correspond to D00 for using register A, D5 for using register B, and then register C is a 10, so we will have 1010 as the least significant bit, so that will make it DA0. And then for register D, it is 1111, so that'll make it DF0. So when we look at these four locations, DF, DA, D5, and also D0, they are slightly different from the rest. Okay, you can see the bit pattern for the rest is a little bit different compared to this one. Okay, there's a 0 here and there's a 5 over here. And but these are hexadecimal digits, so they're hiding a lot of each hexadecimal digit is representing 4 bits, right? So that means that when we see a digit difference, we really don't know how many bits are really different unless we look at the bit pattern behind the hexadecimal digit. But that kind of tells you, how hijacking happens, because the OR AA instruction maps to this particular ROM location, and this is the content at that location. But what this ROM location is doing is the output of this ROM location is configuring the processor to perform an increment operation instead of an OR operation. So the real hijacking is not in the assembler. The assembler could care less, okay? The real hijacking is happening inside the ROM when we specify the bit pattern for location D0. It is different from the bit pattern for location D1 because D1 is a real OR instruction. Okay, it does take both inputs of the ALU, perform the OR operation, and then send it back to the register bank and update the first register specified in the mnemonic, but D0 does not. Okay, D0 takes 1, the constant 0, 1 as into of the ALU, and it also does not update the flags register, and it also uses the it uses the adder inside the ALU instead of the OR gate inside the ALU. So that is where the real hijacking is occurring. All right, so that kind of answers some of the questions that I got queued up after. Well, I think most of these happen in midnight, but I cannot really check Discord the whole day, especially after I sleep, right? So anyhow, so what we'll do today is we are introducing a new topic. So let's go back to Discord, and the new topic, okay, if we scroll down, which is not in exam 2. So what we'll be talking about today, today's Tuesday, and tomorrow, Wednesday, will not be in exam 2. So what we'll be doing at this point is compiling C control structure. We'll start with that, okay? So let's go ahead and take a look at this particular module. All right. So when you look at this module, and you really want to read the entire thing, I was thankful to one of you, okay, I don't want to name the name unless that person wants to get credited, found a mistake in the SR latch description. So the SR latch module is now updated. Now, since that is in the scope of exam 2, you might want to look at it, and I can tell you where the mistake is made to. It has to do with the analysis of the SR latch. I mistakenly used n2.in0 instead of n2.in1 when I describe one of the things that happened. So I can point that out maybe in just a little bit. All right, so getting back to the new topic. This is how a C conditional statement looks like in C or C++ or any programming language that looks like C. So a conditional statement basically has 3 parts. We have a condition, we have a block of code to execute when if and only if the condition is true, and then we have a different block of code to execute when the condition is if and only if the condition is false. So that is, I use curly braces here, because I just want to make the most general conditional statement instead of using single statements for block 1 and block 2. And so in C and C++, there is such a statement type called a goto statement. It is typically not mentioned, or it is not encouraged, because that basically leads to spaghetti code if it is used without discipline. Okay, so what we are doing here is we are structurally translating code from a structured manner to a unstructured manner like this. So now the question is, well, how is it not structured, right? Because this is still using an if, and if itself is structured, we still see block 1 and block 2 over here, and they're still indented. How is this not structured? The structure has to do with the curly braces. So when you see pairs of curly braces, or just braces, the code is structured, which basically means if I have like 3 statements here in block 1, one is a if, one is a while, and the last one is a for, it's okay. Okay. Now in this case, you can see how the braces are gone. So when the braces are gone, I have just flattened this particular structured control structure into something that is unstructured. Okay, now block 1 itself can still be structured, okay, but we can recursively apply this technique to block 1, and then all the blocks within block 1, and all the blocks within the blocks of block 1, and so on until all curly braces are gone. Okay. All right, so let's analyze the new code and see if it is doing exactly the same thing as the old code over here, because they are supposed to be identical. So in the original code, if the condition C is true, then we execute block 1. So we have to make sure that also happens in the in the translated code. So if C is true, then not C is false. If not C is false, we are not going to label L1, and instead we'll continue execution, which is going to be block 1 itself. And after that, we have a go to L2 over here to continue execution by skipping block 2. Go to L2, sorry, I think I said block 2. So there's a go to L2, okay, to skip around block 2, which is the correct behavior, because after you execute block 1, you do not continue execution with block 2 in a conditional statement. So that takes care of the case when the condition is true. What if the condition is false? In the original format, if the condition C is false, then we execute block 2. In the new code, if C is false, then not C is true. So if the condition is true, then we are using the goto statement to continue execution at label L1. And L1 is right over here, which means we'll continue to execute block 2. And this time we do not need any goto, because it would just kind of fall through and continue execution at whatever is after L2. So that way we do not need a goto statement. So occasionally you will see simplified conditional statements without the else portion. Okay, it looks like this in structured C code, and the way we translate it into the flattened C code is like this. I know it looks really kind of the same as the other one, except we do not have an unnecessary goto over here, because basically what happens is block 2 is empty. So if block 2 is empty, then go to L2 really doesn't do a single thing, because it is continuing the execution right at L1, because L1 and L2 basically become the same label without anything in block 2. Section 3.2, I'm just looking at my watch here to make sure that I am ready for the electricians. So I'm going to stop this particular chunk at this point, and if you have questions, go ahead and refer to the part 1 of today's recording, and I'm going to post it onto YouTube, and then I'll give you guys a link in Discord for this segment.